Hello everyone, welcome to another video of my channel. In today's video, we will talk about the geometry of supply chain management. The research for this topic came from my study of manifolds in aquaponics system. The inspiration for this video came from listening to many of the wonderful podcasts of Mr. Scott Luton from Supply Chain Now. In many of his podcasts, there's always a need to measure uncertainty correctly because the only thing that's certain is uncertainty. There's always a need to integrate more variables, and there's always a need to propagate risk, especially when there's a change in the environment, such as um, increase in tariff or a change in policy from a foreign nation. And this video is a combination of many half-baked ideas and probably very silly too of how to satisfy all those needs in supply chain. So our algorithm uses a concept behind Kalman filter. So in standard Kalman filter, we take our observation and then we feed it into our filter to obtain a distribution around the average. You can imagine that distribution as an ellipsoid in high-dimensional space. Of course, you can imagine that as three-dimensional space for visual aid. And the size of that ellipsoid is a measure of the uncertainty in our supply chain network. So once we have our distribution, we use Monte Carlo to do a 7-day rollout or 14-day rollout. Now, this is very similar to how they do hurricane forecasting, right? They would roll out to say 7 days so that various countries and various states can plan accordingly. From the rollout, right, then we try to choose an action that would minimize our cost. Now, notice something that not only are we trying to minimize the mean cost, right, but we also trying to minimize the tail cost, right? The tail costs are the costs that come from work stoppage and stock out. Now, notice something, right? This whole thing is very similar to a very classic safety stock formula, right? You have your main cost and then you have your buffer. So this whole thing, this whole algorithm, right? If you project it onto the one-dimensional demand axis, then you will get your classical safety stock formula. Now, in standard Kalman filter, right, everything has to be linear and Gaussian. But of course, in supply chain, right, rarely are things linear and rarely are things Gaussian. So what do we do? But what we do is that we move in small increment and then we work locally. So then, in such case, right, then we can approximate with standard Kalman filter. In supply chain and as well as in many other fields, we tend to apply some basic machine learning to our data. So what is basic machine learning? Well, at the end of the day, really it's just trying to find a function that best fits your data on average. And what is the process in that basic machine learning? Well, you tend to just clean out your data, you do some kind of dimension reduction, and then you do some kind of feature engineering, and then of course then plug all that into some kind of algorithm, such as say XGBoost or Profit from Facebook. When you apply dimension reduction, such as PCA or UMAP, right, you tend to remove rare events, right, that have yet happened or already happened because you treat it as an isolated event, right? All of that because you ignore the geometry of supply chain. Now, in supply chain, right, the manifold behind supply chain is it's very rugged, right? It's very curved. It has a lot of edges. So the dimension reduction is going to remove a lot of that curvature. Now, because of that, right, mainly you just focus on the average cost instead of the tail risk. Okay, you lost all the tail risk, so you're very fragile to shocks such as tariff and natural disaster, such as a tornado happened near one of your strong vendor. Now, of course, a very experienced CSO can see all this and plan accordingly. Now, furthermore, right, you train your data on lag and compressed KPI. So we'll talk more about this in the next slide. So because of all these weaknesses, it lead to a lot of very catastrophic side effects. For example, one of them is the bullwhip effect, right? So let's say you have an entire line of supply chain down below. They saw a good increase in demand, and so they try to forecast and and then they try to buffer, and the next person line see a big increase in demand, they try to buffer and so on. So by the time I go to upstream, they see a huge a huge increase in demand, and they themselves try to buffer, right? And then of course they would produce way too much items. um, Also, right, when you apply basic machine learning, you just tend to mean fit, right? You miss all the tail risks. So when an event happen, you try to react uh, very late, right? And that reaction may not may not fix things in time, and that action could be very wasteful and without doing anything, and it could harm overall your supply chain. So overall, right, everybody just trying to do their own thing in a very greedy manner, right? Everything is very localized. There's no comprehensive global optimization. Okay, so overall in supply chain, right, is a tug and pull, between responsiveness and efficiency, right, by using pull and push action. So due to all these weaknesses in machine learning, we have a lot of algorithms that are extremely popular, meaning focus on the geometry. For example, geometric machine learning, physics informed machine learning, and probabilistics geometry. So here we talk more about the metrics about delay and compress from high dimensional manifold. So, you have some variables that live in high dimensional space and that can press down to a much lower dimensional space. And you don't get that later until a little bit later. And then you do your forecast based on that delay data, right? And, so when you do forecast based on delay data, then you may not choose the most appropriate action. So let me give you an example of this, right? Let's say I want to test my A1C, right, which tell me if I'm diabetic or not. So the A1C, right, is a one-dimensional projection of all the variables in my body, right? So I get tested, and I don't get the A1C score until maybe a week later. Okay, let's say during that 1 week, right, Krispy Kreme has buy one get 10, and and it's so delicious. I eat, I eat all of them, right? And during that time, right, and during that time, the A1C came back and said that I'm already diabetic, but I didn't know that. And then by eating that donuts, right, my A1C is probably a lot worse now. So there's always a desire to bring in more variables into our algorithm. But one difficulty about bringing more variable is that in high dimensional space, your data points lies at the boundary of your manifold. Um, so, for example, when you take something like the average, right, you get a data, right, that may not even satisfy the business constraint. So something like that would not be very useful, or it could still be in your manifold, but it could become a rare event. Um, so something like the mean and standard deviation, they are not very useful because they measure distance from the center. But in supply chain, we care more about the rational risk, right? Because risk come from a change in the mean, a change in lead time, a change in tariff, etc. Right? So we say that in supply chain, the risks are directional. So in our algorithm, right, what we do is that we try to get an early prediction of that observation instead of waiting for that signal much later. So we make a forecast, right, and then once we receive any new information, then we update our belief. Okay, so um, and then once we have that distribution of our data point. Then from that, we do perform rollout using Monte Carlo. And from those rollout, right, then we choose an action that would minimize the cost, not only the average cost, but the tail costs. There are time and places to integrate machine learning and AI. So, for example, in general, it is very difficult to construct the transition function, and the observation function. In general, these functions require a huge amount of domain knowledge, something that only a CSO possess, right? So what we do is that we construct these functions using machine learning, but we do very basic machine learning, and we let the common filter handle the rest, right? We from the state, from the observation, and then we make prediction using these two functions. Now, the observation are KPI, free index, and policy text, right? So, for example, here this is where we would use AI. Let's say China just came out with some policy that is written out in 10,000 pages long, right? It's hard for us to read that very quickly and extract useful metrics. So what we do is that we use a large language model, right, and let it summarize it and let it extract the metric that we want, and then we plug those metric into our two function, right. So and then we perform common filter locally. We do all that locally, say per site. All right, let's here the site could be the vendor, the warehouse, and so on. And then once we perform the common filter locally, right? We stitch them together in a coherent manner, right? In a cohesive, comprehensive manner. And then once we have our distribution, we roll out to say 7 or 14 days, and then we take the best action. So now we look at the meat of the algorithm. So we make some forecasts, we construct the mean, and then we construct the anomalies. These are used to approximate the tangent manifold. So in low dimensional, low dimensional space, when you work in a field where these manifold is smooth and everything is nice, then you can compute the Jacobian, and that would provide you the tangent manifold, right? But here in supply chain, the manifold are very rugged, very high dimensional, so we can't do that. So what we do is that we're going to work locally. Okay. So again, this is your approximation to the tangent manifold. This is how, very similar to what you did in calculus, where you use the secant line to approximate the tangent line. So because we're going to work locally, we project all our variables down to our local site. Here, the site could be your vendors, your warehouse, port, etc. Okay. Um, so you project it down and you work locally. Now, it could be the case that you are overconfident, so you try to inflate. If you don't inflate, you may miss events that could be catastrophic. So you inflate, and you inflate based on certain statistic, and that we're gonna go over in a second video where we go deep dive into the technicals. Here, this is called the innovation, the difference between the what you observe and what you predict. And then here you construct the anomalies in the observation space. Now, once all that happened, right, you calculate the total observation covariance, right? This is actually another approximation of the observation covariance. And then from that, you do standard Kalman filter, and you get your distribution. Now, so recently I learned something really cool from a paper from Sun and others. So what they do is that, okay, well, in the beginning, right, you approximate or you update based on the best available information, and that's XF. Okay, but when you update, well, now you have you have a better information, right? You have a better center. If you have better information, then you should go through the algorithm again until you get better and better distribution. So this is a Newton process, right? So you only do maybe 2 or 3 times. So in Sun and others paper, they say basically just reiterate until you don't see much improvement, and they look at this. They look at this function, which is the negative log of the Gaussian distribution. So basically, overall, they try to balance between the volume of S and the innovation. All right, so here you try to stitch the increment. Now, this is one part I have to be very careful about in the future. So I do know that we have to stitch the increment because when we did the ensemble, right, the increments are the thing we're trying to approximate. We don't want to, stitch the absolute, state. We want to stitch the increment. So once we stitch the increment, right, of course, then we can construct the all the ensemble easily. Okay. So once we have all the ensemble, right, post analysis, then we, roll out again. We pick the best action that would minimize our costs. Um, so in a company, right, where you have a lot of money and you don't want to have work stoppage or back order or stock out and so on, maybe you want to spend more money on minimizing tail risk, right? So then beta will be increased. So this is more of a buffer because there's so much error, right, in this whole process. There's the error observation, there's the error in the modeling, and so on, right? So we're trying to buffer because there are so many scenario, right, where the distribution could be. So in general, you would this is a cheap thing to do, just basic bootstrap. And in general, you would maybe do this if you wish to perform some kind of expensive action, like do expediting some SKU, or allocate the entire the entire company. Okay, all right. So in here, we talk about all the different geometry that we use in an algorithm. To be honest, this is only here I'm only scratching the surface of the different geometry, the connectedness of supply chain. In general, we all know supply chain is extremely difficult, and I don't think I could ever fully grasp the whole thing, the whole comprehensive viewpoint. So in general, I am a very spatial person. I have to see things, visually, so I can, perform the algorithm and understand better. All right. So deep down below, right, you have your physical network of supply chain, right? This consists of all your vendors, warehouse, port, etc. Okay, and you define a distance between sites. So that distance is a combination of network distance and geographical distance, where we put more weight on the network distance. To construct the network distance, right, we have to bring out all the BOM, um, and then break them to SKU and see which SKU belong to which vendors, etc. That's going to be painful and require a lot of domain knowledge. Um, Now, over your physical network, right, you have your manifold, right? This over here in category theory, right, we call it a fiber bundle, right? We view each site as a single point, and then that single point is packing a lot of information, and that is, we call that a fiber bundle. So here's where your supply chain manifold live, right? It's very high dimensional. We can we can't see them. We can only approximate them. Um, Now, right? So now this manifold is very it's not smooth, right? It is very rugged, very has a lot of edges and so on, but still locally smooth. So that allow us to use Kalman filter in a small increment and local manner. Now, for each point, we have the ensemble of state, and we use that to approximate the tension manifold. Remember, in general, we try to work with the tension manifold to approximate, but that only work if your manifold is smooth and everything is low dimensional and all your function are nice, right? We cannot do that. We can't do that here. So we approximate. Now, so you have your covariance, right, that tell you the uncertainty, but this is humongous, right, and it's impossible to work with. So what you do is you bring it down to your observation space. Now, this is your projection of the uncertainty from the latent space to observation, but we can't really calculate that, right, because p is humongous. Imagine you have thousand variable. This is humongous. It's intractable, not feasible. So what we do is we approximate this with observation anomalies, right? And this right here will be your total observation covariance, okay? And we approximate that. Now, once we have total observation covariance, we can calculate a lot of cool stuff, right? Because its volume will tell us, the how uncertain things are in the supply chain environment, and we can see how the drivers are changing, the driver of your network of supply chain. So how do we do that, right? What we do is, okay, we have this matrix in the observation space. We compress it by using something called singular value decomposition. Basically, instead of looking at the entire matrix, right? What we do is we compress it down by looking at only the top drivers of your supply chain network. And you know um, and each of those is a single point in something called the Grassmannian manifold, right? um, and the sign of each those point, right, tell you how uncertain things are, and the angle of from day one to day two tell you, if whether the drivers of your supply chain change or not. So earlier we said that once we have the um, total observation covariance, we can calculate a lot of cool stuff that'll be useful for executive. Um, so once we have the total observation covariance, right, we what we do is that we decompose them. Now, the the observation space probably still very large, but the due to the fact that this was constructed from low rank matrices, right? There are still ways to decompose them in a feasible manner. That's something we're going to talk about in a different video, right? So once we decompose that, we choose the top drivers, right? So let's say the CSO understand that in their supply chain network that everything depends on top 10 drivers. So we just take the top 10 drivers. From that we calculate the volume, and then also from that we see day to day how the angle change, right? There's a way to calculate the angle. It's called the angle between the principal vectors. Okay. um so day to day we track the volume and the angle, so that tell, okay, whether uncertainty got larger or if the top drivers change. Okay, so I thought this is pretty darn cool. So overall, what's going on, right? So, you have your network supply chain, you got the data, and that's your reality, right? So from all the data, you analyze locally, and then you stitch them in a comprehensive manner, right, to get a global view. Once you have that global view, right, then you try to do rollout and choose, the best decision. Once you have chosen your decision, then you would perform your action, right? So in general, we try to stitch everything together to create a comprehensive enterprise view for decisive execution. Now, if I were to construct this from the ground up, right, because this guy is pretty pretty difficult and maybe made up work in practice. So what I'll do is, of course, right, I'll start um, make everything practical, right? I'll start with SQL. So I will use something like DBT, right, to build all the Go table. Now I like DBT a lot, right, because you can build everything in a modular level, and everything is documented, automatically. It's pretty darn cool, and you can connect that directly to Fabric or Databricks. So right, so here you construct your ground truth, right? This is where all the analysts in supply chain would work on, and then from here you try to extract features so that you could feed it into your machine learning, into data science, that you could perform some kind of prediction, forecast, etc. And then all of that, remember, we use machine learning to help find our transition function and observation function easier, because in general, constructing those functions can be very difficult. And then you could slowly improve those functions as time go along, right? So those will be feed as input into the to this algorithm. I don't think I ever say what this stands for. This is local ensemble transform Kalman filter, right? So here, right, you try to measure uncertainty, you try to do rollout, and then from that you make you choose the best decision. Okay, so this architecture, it's good because if this fail, right, then you still have this layer, and if this layer is not good, right, then you still have this ground truth that everyone will use. So this layer, like I said, it would be for supply chain analysts, and this layer would be used for maybe the CSO, and then this layer would be for a committee of supply chain expert. In data science and in machine learning, there is something that we all assume without us even realizing it, and that's the manifold hypothesis. So for example, let's look at supply chain, right? You can track supply chain using a billion different variables. But really, the effective dimension of your supply chain is maybe around 100. Okay. Um, and that's why we say that supply chain is low dimensional, even though yeah, it live in a billion dimensional space, but really, the its effective dimension is only around 100. The rest are rare noises. So anyone that work in supply chain knows that, right? Because we know that on the majority, things depend on demand, congestion, supply health, policy, weather, etc. Right? So overall, right, the manifold of supply chain, like I said, very curved, very rugged, but still, if you zoom in close enough, right, it's still very smooth, just like the Earth. Um, there's a lot of mountain, a lot of hills and valley, but if you stand at some place, things look pretty flat. Okay, so because of that, we are able to work locally, we are able to infer in the ensemble space, and everything is trackable. And because we move in small increment and we work locally, right, we can apply Kalman filter. So let's connect with something that most of us are kind of familiar with, and that's facial recognition, right? So how is that being done? So let's say you have the face of a billion people. So what you could do is try to take a picture of everyone. Let's say it's 100 by 100 pixel and has three channel red, you know, uh, green and yellow, whatever the primary colors are. Um, so you have three channel, right? So per channel you have, let's see, 100 times 100. That's what, 10,000. So you have 10,000 numbers, right? Each number is between 0 and 255. And because you have three channel, so that's 30,000 numbers that is used to represent a person, right? So that is turned to a 30,000 dimensional vector. So imagine you do that for a billion people. So um, how would you do this? Well, you can turn that into a giant matrix, and then you do PCA, and from the PCA, you take uh, the principal eigenvectors, right? These vector, if you draw it out, it looks like a face, but it doesn't look like anyone. It looks like a blend of many faces. So instead of a billion face, right, you would store these 100 eigenfaces, and right, instead of storing like 30,000 numbers for a person, you store 100 number per person. Um, and because those eigenfaces, they are orthogonal. So if I have a person, right, and I want to know, okay, which person in my database is that person, you can just you can calculate those 100 number easily without having to solve any matrix equation, and that's from the fact that the columns are orthogonal. Okay. Now wait a minute. You're like, wait, why does PCA work here, but not in something like supply chain manifold? because you perform PCA and you find something that can pretty much construct the entire space. Well, because the manifold of faces is very flat with little curvature. Because if you think about it, right, if you take two random person, we all pretty much the same, right? It's two eyes, nose, mouth. There's actually very little difference. So two random person, the difference between them is very little. So overall, right, there's very little changes among the vectors, right? So overall, it's very flat, and so you can use PCA and just take the top 100 eigenvectors, which is something as eigenfaces, and then you can construct almost anyone with just around 100 faces. That pretty darn cool. Now I used to teach linear algebra, and I always teach it in a very abstract manner. But I found out how that was done, right? I was pretty amazed, and all that depends on something called the spectral theorem that you may learn in intermediate linear algebra. So right, but on the other hand, supply chain is not very flat. It's very curved. Um, right. So the union, again, the union, we can view the union of supply chain manifold as, excuse me, you can view the manifold supply chain as the union of all the tangent manifold. And unfortunately, in general, right, the tangent manifold look very different when you go, from one point to the next because due to the curvature. But again, right, the overall, right, is still locally flat, right? So that's why you can approximate, you can just look locally and you approximate the attention manifold with the ensemble. The manifold of supply chain can be viewed as a fiber bundle over the physical sites, right? Again, the physical site or the warehouse, the factory, the port, etc. And again, why is this, right? Because each of those location packs a lot of information, and those information, right, are those that's your latent states. Um, Now, those information, they're not just random set. They pack a lot of information. They pack geometry, they pack metrics, so you can do advanced mathematics on them. Because if it's just a set, you can't really do anything. Now, each side, has its own manifold, right? So the manifold of the entire supply chain network live inside this product space. So this product space is humongous. But because due to all the business constraint, due to the law of nature and so on, this manifold is very small, but it still live inside this ginormous space. Um, so something that we have to do is how do we calculate distance between physical site? Okay, it would be a combination of geographical distance and network distance, and we have to put more weight on the network distance. And why do we do this, right? Because we want to suppress spurious long-range correlation. Now, what does this mean? It means that, for example, a company or a factory in Africa producing, um, rubber washer should have little correlation with a warehouse in Canada storing donuts. Okay, but a factory in Vietnam uh, producing rubber washer should have higher correlation with a factory in China producing metal washer, right? Those should have some kind of correlation. Like I said, and we should put more weight on the network distance, and then in a bit we'll see how to calculate the network distance. So in general, what we do is we break up, take out the BOM, look at all the SQ, and see which HQ belong to which side. Again, this whole thing require a lot of domain knowledge, require a lot of time, and it can be pretty darn tedious. And again, the mathematics behind here is pretty standard. I won't go too much about it, but overall, we focus more on the on the network distance. There's something that called the Gasperi con, where we try to basically we're going to use this to stitch, right, and we have to stitch them continuously, and this function allows us to do that. a major part of the algorithm is to calculate the cost. This is going to be actually very um, time consuming, I believe, and will require a lot of domain knowledge, which is something I definitely do lack. Um, so I think in general, probably just to look at maybe the top SKU or higher, depend on the company. And then we put weight on the SKU, right? Maybe certain SKU are much more important than the other one. So those are one that we definitely don't want to have a shortage of, right? Um, and of course, the total of the weight should be one. And there are various, KPIs, metric that we need to keep track of. For example, there's the fill rate, there's the back order, there's the time until recovery. All that somehow combine into the cost. So you would, add up per SKU here, right? Add up all the total cost over all the SKU, right? So this would be all the measured services and shortest loss, and this is the cost of performance and action. Maybe require $1 million to buy some new product, or $1 million to allocate something, or some kind of action. Now there'll be another cost where called terminal costs. These are the costs that are beyond the horizon. For example, you roll out 14 days, but there are still things that are not yet fully fixed. For example, you haven't totally recovered yet. You haven't received the all the order and so on. Right? These are the terminal costs. So again, we have this cost function. Okay, we have this cost function that take state and a action, right? And that gives us some cost. That's a real number. And then we have the terminal cost, right? Again, from the manifold to real number. Now, there are two type of action. The action that are expensive to execute, right? These are the pull lever. And then there are actions where we just maintain the company, right? Those, I guess, are more a kind of a push lever. So, first you would take some kind of expensive action if you have to, and then after that, see how things roll out the next few days, based on some base policy. So this is very similar to reinforcement learning. So then the cost per action, right, is the geometric of the all these costs, okay, and plus the terminal cost. Now, again, why do we have this discount? Well, because the action, right? Excuse me, because of the prediction get worse and worse, right? We should put less emphasis on the later forecast, but put more emphasis on the all the recent forecast. Okay, so we have this distribution of costs. Now, to be more robust, right, we need to have more, I guess, more samples. So what we do is we have a sequence of link n, right, noise path. So these are the things that contribute to the uncertainty in our pipeline, right? So you would draw L of them, or however, how many you want, and then basically each ensemble is a scenario, okay? And then what you do is you perturb each ensemble, a little bit by adding up all the noise, right? So because you have, let's see, K ensemble members in L path, right? So you have a total of N noise sample, right? So I guess the more the better, right? So we have this distribution of the cost. All right. So we have this, using Monte Carlo N rollout cost, okay? And then, from that, we take the compute the C-var. Basically, just look at, say, the top 5% of the cost and take the average, okay? These are the tail costs. Now, then you perform a bootstrap. What you do is you sample beta, right, from these rollout, okay? And so from that, you construct the standard error, and that's going to be your buffer, okay? So your cost function is going to be the average cost plus tail cost plus this buffer, okay? Um, so now So again, right, we have two kind of action: the expensive action and the baseline policy. Right, these are the action that you take to maintain the company, make sure the company is running. Again, we have this cost function. Now, we need to calculate the value of the action, right? So we would only take an expensive action if the cost is lower than than using the baseline policy. Okay, and so in general, right, we would only perform that action if the the gain of the action is more than the cost to perform that action. Let's say you take $1 million to perform some kind of expensive action, and the improvement is 100,000. Then you don't want to take the action. But if the action save you $5 million when it costs only $1 million, then definitely you do want to take the action, right? So what you do is choose an action that would minimize the cost, okay, over all the different costs, over all the different action. All right, so overall, this is our algorithm, right? We have some forecasts, we perform some analysis, right? And again, we also recenter that would make things more robust. And so we have this distribution, right? This empirical distribution. From that, you do 7-10 day rollout, right? And again, it's up to the company to decide, okay, do we care a lot about the tail risk? Then we put more weight on it. And whenever we perform an expensive action, right, we want to have more scenario. Okay, so we have this buffer before we perform the action. Okay, and again, if the company doesn't have a lot of money, right, then we we reduce this weight on the tail cost, and we're like, okay, it's okay to incur some kind of tail cost, and that's fine. But again, that tail cost could be service level agreement that you don't meet, etc. Right, so you want to maintain some kind of service level, and if you have money to manage, right, again, right, you want to incur that cost so that you maintain that service level to another company, and then you take the action and then continue the process. So this concludes this overview video of the algorithm. So I guess in the next video I will go into more in depth of certain things like how to tune, how to set up, more deep into